Okay, let's start. But I'd still like to do some kind of review from what we did from yesterday's class. First thing, I told you that, I mean, if the initial equation given by, like say, P naught n plus P naught equal to 0, you know what P naught and Q naught are. If I have the roots of this initial equation given by your m1 and 2, and if your m1 and m2, if they differ by an integer, so we may not be able to straightforwardly find out the second linearly independent solution. So definitely, I mean, corresponding to one of those m1 or m2, we are able to find out one series solution. That is definite. But as you have seen yesterday, finding out the second series solution is not that straightforward. Okay, so obviously, if the difference between m1 and m2 it is not an integer, definitely we are able to find out the second linearly independent solution in terms of a power series. Okay, and then yesterday we saw that I had given you evidence that if your m1 equal to m2, then what happens once you have found out a series solution, say y1, then the second series solution, y2, it can be found as this. It can be found as this. Like say if x to the power, because m1 equal to m2, whether I write m1 or m2, it doesn't matter. And then Cn x to the power n. And then, if you recall, I told you that it should start with n equal to 1 to infinity. It's to start with n equal to 1 to infinity. If I start it with n equal to 0, definitely I will write that C naught, it is equal to 0. Okay. Yesterday I told you that I am almost 99.5% sure, I guess, right? So, did you check yourself for the remaining 0.5%?
Yes, sir.
Am I right?
Yes, sir. Yes, sir.
Okay.
Sir, actually, C naught term will be A naught B naught divided by minus K plus 1.
But again, I think you were still trying to do it right from the beginning. Like say, I know what you were doing. You were doing from B naught x to the power minus K plus 1 by K plus 1, right? And you worked it out. Okay. So let me try to convince the others what was happening. Let me get back to what we did yesterday. So yesterday, if you recall, I was trying to find out the second series solution from this concept, your y1b, right? And then I have found out that your v, it turns out to be something like this, x to the power minus k plus 1 divided by this, and here I think b k minus 1 ln x plus was it bkx? Bkx, right?
Yes, sir. Bkx. Yes, sir. Bkx.
Okay, fine. This is good enough. Okay. So, and again, I assume that your k was equal to m1 minus m2 plus 1. Okay. And the rationale behind choosing k to be like that was because I want to make sure that the difference between these two roots, m1 and m2, of course, I have assumed that m1 is greater than equal to m2, right? The difference between them always remains a non-negative integer, right? So now, if m1 equal to m2, then you know that k equal to 1, and then I had already shown to you that in that case, your bk minus 1, this is going to be equal to b naught. Bk minus 1 is going to be equal to b naught. Is it okay? This I did yesterday, right? Okay. So, and of course, B naught is not equal to 0. So, what that is going to do, that is going to guarantee, in fact, that is going to guarantee me the presence of a logarithmic term in the second series. Okay. Now, what we are going to do here, just look at this. Just look at this. So now I have found out that, I mean, my k minus 1 itself is B naught. Okay. In case when m1 equal to m2 not every time. Remember that. Okay. So then what is going to happen? This series itself is going to start. With B naught. Is it okay with everybody? Right? Because this series always starts with the constant B naught, isn't it? Right? I have now found out that the B naught is nothing but the coefficient of the logarithmic term here. Okay? Is it clear to everybody?
Yes, sir.
Yes. So that is why what is going to happen now here, this is simply going to be B naught y1 ln x and then plus y1 into the remaining series. Y1 into the remaining series. Like say this b1x plus b2x squared and so on. Okay. So now what is happening here? This is fine. B naught y1 ln x and then here this y1 is something like your just a minute. Y1 is something like x to the power, whether it is m1 or m2, it doesn't matter. And then your an x to the power n, fine. And then this is simply what is going to happen. Maybe n equal to 1 to infinity, b and x to the power n, right? So then you know that if I expand this is simply so a naught and this is b1x and so on, right? So that means if I write the product of these two series, these two series, I must have the constant term in that series as 0, right? So that is why I am always going to have it in this form. Is it clear now? Okay, fine. So now I am going to show you. Today I'm going to discuss a lot about some relevant topics. Okay, which you probably haven't thought about it earlier, but it is really important. Like say we just tend to neglect it, not really neglect. We just don't bother about that. But I think as a PhD student, you should know that. Okay. Now let me show you that theorem again. Okay, I'll just let me get back to this theorem. Okay. So yesterday I have already described it. In fact, now what I have done, I have already proved the first part of the theorem that okay, I can have a series solution of the type 6 and 7. I can have a series solution of the type 6 and 7. Okay, in the case when m1 and m1 minus m2 is not 0 and positive integer. And I have besides that, I have also shown you how to find out a second series solution in case m1 minus m2 equal to 0 or a positive integer, right? What I didn't do is the last part here. If you look at this, again this series a n x to the power n converges for mod x less than r. Okay, so what you have to do now, you have to prove this one. So because I have already done similar kind of proof for ordinary points, what I suggest that you just look through Simon's book. There is an appendix, I think it is appendix B or something like that, around page 210. You just please do it on your own, taking help of Simon's book. It is similar to whatever I have done earlier, so it shouldn't trouble you that much. Okay, slight difference is there, but I think you'll understand it. Okay, please do that. Okay, so now next slide that I'm going to show you, it is going to give you a summary of the solution of a second order linear differential equation, with regular singular points at the origin. Okay, so this is simply the summary of all the data. So here is that. Like this, you already know. What is happening here. So as you know, what they have done, they have adjusted it here itself, xpx and x2qx. So that shouldn't bother you that much. Okay, although what I did, I wrote it in the normal form, but you will understand it. And you know that instead of m, they are simply writing r here for the initial equation. Okay, and see again here you will see that they are considering the interval where x is strictly greater than 0 or where x is strictly less than 0, and that is because we are trying to find out a series solution in the neighborhood of the origin. Okay, remember origin is a singular point. Fine. Okay, so this one I have already done. Right? So definitely one solution is going to exist. You know that. And here they are writing coefficients in terms of the roots of the initial equation, and that also shouldn't bother you. Okay? And what they have done, as I have told you earlier, the very first constant a0, it is generally taken as 1, because ultimately when you find out a general solution, you are going to come up with some constants, right? And that is why even if you write a0 equal to 1, it is going to be absorbed by those constants there. Okay, so this is about the existence of the solution, irrespective of whatever is happening to m1 and m2. Definitely, I will be able to find out a solution, series solution. So now the next phase here, it talks in detail about the second series solution. Okay, see here if r1 minus r2, in my case, if m1 minus m2 is not 0 or a positive integer, then in either of the intervals, these two intervals, either x is less than 0 or your x is greater than 0, within the radius of convergence, you will always be able to find out a second series solution. This I have already told you. Okay, fine. And you know that all these coefficients, they will be determined by some recurrence relation. We are already aware of this. Now here 23 is important. So now you see here. See if the roots of the initial equation are equal, so then the second solution is given by this. Okay. So they are taking mod of x, because in case x is negative, this is going to accommodate that as well. And here this is important. The second term is important. Here you can see that. See they are starting from n equal to 1, as I have told you just now. Okay, fine. And somebody wants to say something? Okay, fine. And again, if it is a positive integer, this also yesterday I have already found out. So what this is about, this ln x, again it comes up with a. Here that a is nothing but the constant bk minus 1, where we are assuming that k is not equal to 1 now. Okay, I think now it is clear. In this summary part, it is clear. Okay, fine. So okay, we have done a lot of stuff, and like say, I'm thankful to you for bearing with me, because they're kind of boring and kind of monotonous, right? But again, they tell you a lot of story. And now I would again like to come back to something. And I know that you people are, I'm not sure because I haven't seen you all in person. So, but from my experience, I can tell you that, I mean, the students, what they do, they, I mean, simply attend the classes and just before mid-sem, end-sem or quiz, they start studying. They don't do anything immediately after the class. Okay, I'm going to perform a test now. Yesterday, if you recall, I had, okay, see from the equation this one, y double prime plus 3x prime plus qx y equal to 0, and assuming that x dx and x squared qx, they can be expanded as power series about x equal to 0, and if we assume the series solution of the given equation as the Frobenius series, and then from there I come up with some reference relation. I'm simply going to write maybe, let us see what I can do. Then A1 will not plus A naught, I think this is M P1 plus Q1, right? This is equal to 0. I'm writing this because, as you know, I always have some hidden agenda. Is it M plus 1? I think it's M plus 1. What is this? This is P2. I think Q2 plus K naught. I think MP1 plus P1. Is it okay? No, it starts with just it increases like this. So this is going to be this is equal to 0. Okay. And again, I'm telling you because this is fine. An minus 1 plus n plus n p naught plus p naught, and then again just a minute. What I did, this is A naught, this is A1, so A naught M what it is Pn plus Qn, and eventually I'm going to find out A n minus 1 n plus n minus 1, okay, and again here P1 plus P1. Okay, fine. As I told you, I have some agenda behind this. Why I am doing this? Okay, fine. So yesterday, while developing the theory, during our discussion, so what I told you is that when your m1 minus m2, say, suppose this is a positive integer, this is a positive integer, or 0 for that matter, 0. So then, what happens if it is a positive integer? Say it is strictly a positive integer. So then, what I told you is that this expression, I can write it as a n f. Say suppose I have found out the roots of the initial equation as m1 and m2, and suppose I am trying to find out the series solution corresponding to m2. So then this is going to lead me to something like this, okay? And then I told you that this is going to be equal to minus of this, say A naught M2 Pn plus P1 and minus the A n minus 1 M2 plus n minus 1 P1 plus P1, right? I told you this. Okay. So then somebody stopped me in between, like say, again, that was a very valid question. Somebody couldn't figure it out. I remember that. So what was happening? I told you that obviously, because M2 plus N equal to M1, right? And f of M1 is already equal to 0, M1 being the root of the initial equation. So definitely from this part, 0 is going to come. Okay? You remember this?
Yes, sir.
Yes?
Yes, sir.
And then I told you that what happens? This right hand side, sometimes it may become 0, sometimes it may not become 0, right? And I told you that if it becomes 0, I'm fine. I'll be able to find out the second series solution somehow, right? I told you that you simply plug in a n equal to 0 because you have got infinite choices for choosing the value of a n, and even if you take some other values of a n, it is even going to work, and then you can continue the process. But if the right hand side is not equal to 0, then we cannot proceed further, right? The second series solution you cannot find. My question to you is that, did you actually try to figure that out with some example? Did you try to figure it out with some example? I know from your silence, I know that your answer is no. I-K-N-O, you know that your answer is N or no. Okay? Fine. So let me give you 2 examples on that, because it is very, very interesting. And that concept will be crystal clear to you. Okay? So that is why I am doing this. So now let me go to your Bessel's equation. Your Bessel's equation, if you recall, here I am writing. Right? This is Bessel equation of, say, order P. Is it okay? Fine. Now, suppose P equal to, let me first take maybe, okay. P equal to 1. Suppose P equal to 1. Okay, fine. So then, that means what are the roots of the initial equation? Yes. What are the roots of the initial equation? See, anyway, here what is going to happen? Like once you divide it, say y double prime, so 1 by this plus 1 minus, okay, no problem, p squared by x squared y. So this is equal to 0. Then what is going to happen? Your if you, so this is px, this is qx, okay? So your x px, this is simply equal to 1, right? Is this part okay with everybody?
Yes, sir.
Yes, sir.
Yes.
Yes.
So similarly, thank you. X squared qx, this is simply, let me write it as minus p squared plus x squared, right? So then, if you think in terms of the series, like say p0 plus p1x, etc. For this, so basically I am getting p0 equal to 1 and p1, p2 everything is 0. And similarly here, again, if I compare it with plus p2x squared and so on, here my Q naught is going to be equal to minus P square, and your Q2 is going to be equal to 1. That is important. Q2 is going to be equal to 1, and then what is going to happen? All the remaining, Qi, it is going to be 0 for all I not equal to 0, not equal to 2. Is it okay? Fine?
Yes, sir.
Yes, sir.
Yes. So, you will see that the initial equation, it is eventually like m square minus p square equal to 0. M square minus p square equal to 0, and that gives you m equal to plus minus 2. That's it. Is it okay? Fine. This is pretty straightforward. Don't worry about it. You can easily get that. Okay, fine. So now let us come to this point. I am still into Bessel's equation. So that means when your p equal to 1, I am having, say, m1 equal to 1, m2 equal to minus 1. Is it okay? Fine?
Yes, yes, sir.
Right? So that means my m1 minus m2, this is equal to 2. It is definitely a positive answer. Fine? Clear? Okay. So now let me try to find out the coefficient a2, a3, etc. Because a0 anyway, I'm going to assume it as simply 1. Okay? So now look at this. Now look at this. What is happening? Okay. So from the first equation, what we are getting now, say I am trying to find out the series solution corresponding to m2 equal to minus 1. Okay, assuming that I have already found it out for m1 equal to 1. Okay, so then what we are going to get from here, definitely since m is minus 1, this term and this term will go. Right? Is it okay? Isn't it?
Yes, sir.
Yes? Okay, fine. So I am going to get, say, a1. What is q naught? Q naught is minus p square, right? So that means q naught is minus 1. So a1 into minus 1, and again from here what I am going to get? P1 is 0 and Q1 is also 0. Is it okay? Just simply look at this. Here. From here I have found out that P1 is 0. From here Q1 is also 0. So basically I am going to get A1 this equal to 0, isn't it? A1 equal to 0. Is it okay?
Yes, sir.
Yes, sir.
Fine. So now once I reach this step, say A2, this is nothing but this part is nothing but f of m2 plus 2, isn't it? This part is nothing but f of m2 plus 2, isn't it?
Yes, sir.
Fine. So that means this is f of m1, right? So obviously this part is going to give me 0. I am not going to even calculate it. Is it okay? Fine. Now, if I look at the second part, you know that both P1 and Q1 are 0. So this is going to give me 0, right? And here definitely P2 is 0, but Q2 is 1. Is it okay?
Yes, sir.
Q2 is 1.
Yes, sir.
So I am going to get from here my A0, that is already 1, and your M is simply M2. So M2 is your minus 1, and P2 is 1. So I am getting this. So this is equal to 0. So now I'm not going to put this is equal to 0. So I'm going to put this was my left hand side. So my right hand side becomes minus of this. So now from here, you can see that although the left hand side is 0, the right hand side is not equal to 0. Does it convince you now? Does it convince you now the fact that sometimes the right hand side can be non-zero, sometimes the right hand side can be 0? Is it okay?
Yes, sir.
Fine. So that is why corresponding to P equal to 1, you cannot get a second series solution. Okay. But I am leaving this a homework. If you take this P equal to half, P equal to half, then I am going to have M equal to half, M1 equal to half, M2 equal to minus half. So this is going to be equal to 1, right? So then from the very first equation, you can see that everything is going to come out as 0. Because see here, so now I'm going to do it for simply f of m2 plus 1, isn't it? Are you getting my point or not?
Yes, sir.
Right? I'm going to get it for f of m2 plus 1, isn't it? And that step is nothing but this step. That step is nothing but this step. So here you can already see that P1, Q1 are 0. So this part is definitely going to give me 0. And F2, f of M1, that is already 0 here. So both part is going to give me 0. So, I mean, it will be possible for you to find out the second series solution. Is it okay? Fine. So now I think this concept should be absolutely clear to you. Okay, what happens when M1 minus M2 is an integer? Okay, fine. So now I'll still be there in the Bessel's equation. In your syllabus, you have Legendre's and Bessel's I think functions. Of course, they will be coming from Legendre's and Bessel's equation. And probably both in your BSc and MSc, you have done all the properties of Legendre's and Bessel's functions. Okay. So I'm not going to do anything with the properties. So what I'm going to do, I am going to, like say, give you. See, so far we have already done solution of Legendre's equation, right? Through the ordinary point approach itself, we have got. Okay. What I'm going to do, I don't know whether time will permit me today or not. I am going to do Gauss's hypergeometric equation, and from there I'll try to find out. At least I would like to reach. I'd like to reach Legendre's polynomial from there. Okay, fine. And again, continuing with what we did earlier yesterday and what I have told you today regarding indicial equation having equal roots, what happens there. So from there, right now, I will try to find out what happens when the indicial equation from Bessel's equation gives you equal roots. Okay, and what kind of solution you get out of that. And you have already done, see, Bessel's equation, I don't want to again solve it because it is pretty straightforward. You know the procedure now, right? And you must have done this earlier also. Okay, so now, can you tell me, just simply by looking at this Bessel's equation or whatever I have done, when are going to have, equal roots? From this Bessel's equation, when are you going to have equal roots?
P0.
P0, your
But
true is already here, right? Bessel's equation is always going to give you m equal to plus minus p. So in order for them to be equal to 0, you must have p equal to 0. So basically what I'm going to do now, I'm going to solve Bessel's equation of order 0. So I'm going to plug in p equal to 0. And see, when p equal to 0, when p equal to 0, then your simply this is going to be, this is equal to 0, and from here, this is simply x squared, and here even q naught is also equal to 0. Is it okay? So basically here qi is equal to 0 for all I not equal to 2. Is it okay with everybody? Fine?
Yes, sir.
Yes? Okay. So now let me try to find out the recurrence relations. Okay? So two equations will be good enough. Huh? Okay, let's be not. This I have already made use of. I can do this, but I can. The initial equation also I don't need now because I'm not going to use it. I'm always going to assume that a not equal to 1, and from the recurrence relation I am going to find it. So a n also I have removed that, but anyway, I think this should be good enough for me. P1, P1. So A1 from here, you can definitely see that A1 is going to be 0. Isn't it? Right? Because say P1 is 0, this is going to give me 0, right? And anyway, this is say this is simply what? Whatever may be the value of this, since this is equal to 0, I am always going to get A1 to be equal to 0. Is it okay? Fine?
Yes, sir.
Yes.
Yes, sir.
Right? Whatever may be the value of this, I am going to get A1 to be equal to 0. So A1 equal to 0, I am assuming A not equal to 1. A not equal to 1. And then now let me concentrate here. A2. So A2, so M is 0. Okay. And see Q naught is 0, right? And so I am going to get from here P naught equal to 1. P naught equal to 1. Q naught is 0. So I'm going to get A2 2 plus 2, right? Yeah, I'm going to get A2 2 plus 2, and then P1, Q1 both are 0, so this is anyway 0. P2 is 0, but Q2 is equal to 1. So I'm going to get from here A naught equal to 0. So this is going to give me simply A2 equal to minus 1 by 2 square A naught. This is fine. This is fine. And what about this one? This was n plus n minus 1, and then plus n plus n into P naught plus Q naught plus A naught m Pn plus Qn plus A1 of, I think, n plus 1, the n minus 1, and eventually, just here I would like to add one term, so please bear with me. This I don't need anymore, and let me find out whatever I need. Okay, so eventually here a n minus, so n plus n minus 1. So this is the q1 plus q1. I'm not even bothered about it. What I'm bothered about is the previous term, a n minus 2. So this is going to be m plus n minus 2, and this is going to be p2 plus q2, because say q2 is not equal to 0, right? So that is why I'll be interested in this term. Is it okay why I have written that down? Fine. So then what you can do is that, like say, except for this one and this one, see, this one involves both P naught and Q naught, right? And this one involves Q2, right? So that is why all the other terms inside the bracket, they are going to give me 0. Is it okay with everybody? Fine? Okay? So this implies an, so because m is 0, so from here n into n minus 1 plus n, because p naught is 1, q naught is 0, and from here plus a n minus 2, again this is 0, q2 is 1, so this is equal to 0. So from here, and again from here, I am going to get n squared. So basically, I am getting n squared a n plus a n minus 2 equal to 0. So this implies a n equal to minus 1 by n squared a n minus 2. Is it okay with everybody? And of course, this is for all n greater than equal to 2. Is it okay? Fine?
Yes, sir. Yes.
Yes. And you will see that if n equal to 3, so this is going to be in terms of a1. a1 is already 0. So what is going to happen? All the odd terms, all the odd, coefficients with odd suffix, they are going to vanish. Is it okay? Fine. So only the even terms here are going to remain. So that brings me what? Your, okay, so now I can do away with this. Well, I'm doing this because this is an interesting example. And still it hasn't unfolded. There is still the second part to it. So now I can okay, everything I can remove. Yes, okay, fine. So fine. So now I'm going to concentrate only on even terms. So this, so A2, I have already found out A2 equal to what? 1 by half square A naught. A4 equal to 4 square A2. And from here I am going to get what? Minus 1 by 2 square. Is it 3 square? 4 square. 2 square into 4 square A naught. And similarly, A6, I'm going to get what? The minus is going to go. So minus 1 by 2 square, 4 square, 6 square, a naught. Of course, a naught, I'm going to assume it to be 1. So now from here, what I can do, you can take it to be like, say, a 2 into 3, right? And this is minus 1 cube. So now, say, this is what? 2 square, then 2 square into 2 square, 2 square into 3 square, right? And from here, how many? 2 square into 2 square into 2 square. So that means 2 to the power 6. So 2 into 3, and then 1 into 2 into 3 whole square. So that means this whole square. Fine? Sorry, this is cube. So that is why I can write it as a, like, say, 2n. So this is going to be minus 1 to the power n, and then 2 to the power 2n, and then factorial n whole square. Is it okay? Fine? Of course, I'm taking a equal to 1 and a not equal to 1, and from there I'm getting this. Okay, so what does it give you? What does it give you? So I can write the first series solution. I can write the first series solution as this 1 plus, maybe I can write it as n equal to 1 to infinity, and then minus 1 to the power n, then 2 to the power 2n, 2 to the power 2n, and then what? Factorial n squared, and then, yeah, you please tell me, what should I write here? X to the power
2n.
2n. X to the power 2n. So this is equal to 1 plus 1 to infinity minus 1 to the power n factorial n square x by 2 whole to the power 2n. Okay, if I plug in n equal to 0, this is going to give me 1, right? If I plug in n equal to 0 here, is it okay with everybody? Because factorial 0 is 1, this is 1, x to the power 0, anyway this is going to give me 1. So basically I can even write it from n equal to 0 to this. Is it okay? Fine? Yes?
Yes.
Yes, okay, fine. So this is about finding the, like, say, you know that definitely we will be able to find out one series solution. So now, what about the second solution? What about the second solution? Okay. So, okay. So now you know that if I have equal roots, the second solution, it can be found like something like okay. And in case of equal roots, definitely here C naught has to be equal to 0. Is it okay? Fine? Yes?
Yes, sir.
Yes? And because here M1 and M2 both are 0, so that is why I can remove this term, right? Right? Because x to the power 0, this is going to give me 1. For this particular case. For this particular case. Yes? Fine? So see, now what I'm going to do, I'm trying to find a solution. I'm trying to find out the second series solution because I know that for equal roots, definitely it is going to exist and it is going to be in that form. Okay, fine. How to go about it? Can you tell me? Can you just give me some way how to find out the second series solution from here? See, I can simply write it like this. I can simply write it like this. But the thing is that you have to give me. What the coefficient Cn, right? I have to completely find out the series like the way I have found it out here, isn't it? Okay. What I am going to do, this relation, because I have already seen that y2 is a solution. What I'm going to do, I am simply going to find out the first order derivative of y2. So then this is going to be what? Fine. Okay. And from here, and going from 1 to fine. Okay. Then y2 double prime. Again, what is going to happen here? This is going to give me what? Okay. Fine. Okay. From here, okay. Fine. So far, so good. So why I'm doing all this? I mean, is it giving me a hint how I'm going to find out? Yes, those coefficients Cn.
We'll plug it in that equation, our original equation.
Yeah. So now, because you know that your y2 is also a solution, right? So what I'm going to do in the original equation, if I plug in this or Bessel's equation of order 0, this plus x squared y2, right? So this should give me 0. Is it okay? Fine. So now this is equal to what is going to happen? If I multiply it by x squared, and again say these two together, this is fine. So I'm going to get minus y1 plus 2x y1 prime plus x squared y1 double prime ln x. Okay. What I'm going to do that all this series. Let me write it here. And then once you multiply it by x squared, this minus 2 will be gone. So n equal to 2 to infinity n into n minus 1 Cn x to the power n. Okay, right? So this is y y2 double prime. Okay, and now let me come to this, multiply it by x. So that is going to give me plus y1 plus x y1 prime ln x, and then here plus again n going from 1 to infinity. As you multiply it by x, this is going to give me x to the power n. Okay, and then your this x square y2. If you multiply it by x square, so I am going to get x square yn ln x here, and from there, n going from 0 to infinity, your Cn x to the power n plus 2. Is it okay with everybody? Fine? Yes?
Yes. Yes.
Okay, fine. So probably you have now, you know the trick. So obviously these two terms goes out, and here if you take ln x common, then from this what you get? Simply ln x and then this one x square is, isn't it? Fine. And since y1 is also a root of the original Bessel's equation of order 0, this is going to give you 0, right? So basically we will be left with this term, and now I have to work with this. Is it okay? Fine?
Yes, sir.
Okay, fine. So now let me try to work out with that. So now what we can do, I'm simply, I'll write it down systematically. Okay, fine. So now that is going to imply me, this plus this is going to be equal to 0. Fine. So now just bear with me. Yeah. So now see, if you plug in n equal to 2, here the highest power, it is x squared. N equal to 1, this is x to the power 1. And n equal to 0, this is x squared. Fine. So basically I have fine with this one and this one, but I have to take one term out of this. Is it okay with everybody? Fine. I have
Yes.
to take one term out of this. Okay. So let me take that one term. So that is going to give me plus C1 x. Okay. And then now let me start from here. So n equal to 2 to infinity, 2 to infinity. So n into Cn, and again it starts from, as I have already taken this out, n equal to 2 to infinity, and again n Cn x to the power n. So plus n. Okay, and then what about this? See, if I plug in this equal to p, then when n equal to 0, p is going to be equal to 2, right? And n is p minus 2. So basically, this is c n minus 2 . Is it okay with everybody? Fine? Yes? I can erase this, right? Yes? Yes? Anyway, you have the videos of my recording of my lecture, although I have seen that nobody even bothers to watch them. So I don't know whether they are helpful or not. Okay, fine. So this gives me, like, let me, so C1x, so n equal to 2 to infinity, and then this is the n square minus n plus n. So this is the familiar formula. N not 0. So okay. So see minus 2x y1 prime. And if you recall, my y1 was what was that? Let me write it like this. Intentionally, I'm writing this because I don't want any confusion with the constant term. I have that, right? What y1 was that? Is it okay?
Yes, sir.
Y1 was that. So now if you take derivative of this, so obviously y1 prime, this is going to start from 1, and then this 2n is going to come here. Is it okay? 2n is going to come here, right? And this is going to be 2n minus 1. Is it okay with everybody? Fine. So what I have got 2x. If you multiply it by x, this minus 1 will be gone. So basically, let me write it down once, and after that I'm going to make it clear. And equal to 1 to infinity, and then 2n minus 1 to the power n, okay, n squared to the power 2n, and x to the power 2n. Okay, fine. So now let me adjust these terms. Okay, let me adjust these terms. Okay, set here minus 1, then minus 1. I can accommodate with this. I can write it as minus 1 to the power n plus 1. Is it okay? Yes?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay. So I'm going to adjust this here. Okay, fine. And these two, again with these two, this is 2 squared. Let me bring it here. So this is going to be 2 to the power 2n minus 2. Fine? Okay, fine. So now what I'm going to do, I'm going to equate the coefficients of different powers of x on both the sides. So if you do that here, obviously the very first power of x starts with x squared. Is it okay? Fine?
Yes, sir.
Yes, sir.
Yes? X squared. So that means your C1
Sir,
must
is
be
it
equal to
x raised to power 2n minus 1?
uh-huh. No, I multiplied it by x, no? Because this 2x was there.
Oh,
If you
okay.
recall it, I multiplied it by, that is where I got x to the power 2n.
Oh, okay, sir.
Huh? So that means C1 equal to 0. Okay. So now from n equal to 2 to infinity, if I work it out, then you will see that what is this for n equal to 2? This is going to okay, fine. Or yeah, just give me 1 second. Now how I can adjust this? Okay, this is done. Now here also, what I can do, if I write n equal to 2m, then what is going to happen? It is going to give me 2m from 2m equal to 2 to 2m squared c 2m to m minus 2 x to the power 2m, and then m is going from 1 to infinity, isn't it? Fine. So basically what I can do, I can simply, because m is a dummy suffix, I can do it like 2n minus 2. Because see, I could have continued with simply n. But again, I would have to do some extra calculation, because in that case, what your C1, C3 all are already 0, isn't it? Fine. It's
Yes,
totally
sir.
different, right?
Yes.
They are all 0. So what I can do, because I have already found it out that C1 is equal to 0, right? So I can simply use this formula. Okay. So if I use this formula, so for n equal to 1, this is going to give me 2 squared C2 plus C0. So now what you do, simply plug this in here. You forget about x to the power 2n. My job is easier now. That is what I mean by saying, by converting this, into an even order series. Okay. So then, so this is going to give me what? This is going to give me what? N is 1. So 1 into minus 1 square. So then 1 square, then 2 to the power 0, 2 to the power 0. I don't even worried about this, because that will be accommodated. So what I get, so C naught, it was already 0, because the roots of the initial equation are the same, equal. So from here I will get C2 equal to what? 1 by 2 square, isn't it? Is it okay? Fine? Yes? Okay. Then plugging in n equal to 2, this is going to give me 4 squared C4 plus C2. This is equal to n is 2 now, minus 1 cube. I'm just going to do, 2 squared, then this is again 2 squared, right? So this implies C4 is going to be, say, C2, this was 1 by 2 square. Okay, fine. See, let me bring this 1 by 4 square here. Okay, if you transpose C2, that is 1 by 2 square, once it goes to the right hand side, that is going to be minus, that is going to be minus, and that was 1 by 2 square, and again, this is minus, so that will be accommodated with this. So this is going to give me, let me see what is there. Okay, let me tell you what it is giving me. See, this one is what? 2 square. This one is basically 2 square. So these 2 will go out. So this is 1 by 2 square into 2. 2 square into 2. I'm just trying to find out the pattern. So from here, what I'm going to get, this is, if you take 1 by 2 square out, this is going to give you 1 by 2 square into 4 square, and then 1 by 2 square, if you take it common, this is going to give you 1 plus half. Okay, so I'll just simply do one more term, then you know what the pattern will be. Okay, so now again from here, if I take n equal to 3, then I am going to get 6 squared C6 plus C4. This is going to be n equal to 3 and then minus 1 to the power 4, and then your factorial 3 squared, then 2 to the power 4, right? 2 to the power 4. So this implies C6, this is equal to 1 by 6 squared, right? Now C4 was negative here. Once you transpose it to the right hand side, this is going to be positive. So it is 1 by 2 squared into 4 squared, 1 plus half. This is already positive. Now, see what is happening here. This 2 to the power 4 is simply 4 squared. Is it okay with everybody?
Yes, sir.
Fine.
Yes,
I
sir.
hope I am not alone here. Okay. So then, if you look at these two terms, factorial 3 is simply 2 into 3. So this is 2 squared, 3 squared, and then this 3, this is going. Fine. So this is going to be your 2 squared into 4 squared into 1 by 3. Is it okay? Is it okay?
Yes, sir.
Yes, sir.
Fine.
Yes.
So that means now I think I can get rid of this. I can get rid of this. So again, my pattern is coming out. This is simply 1 by 2 square, 4 square into 6 square, and then this is 1 plus half plus 1 by 3, right? See, this I can, this I can write as minus 1 by 2 plus 1. This I can write as minus 1 to the power 3 plus 1, and so on, right? So then C2n. So this gives me an idea that C2n, this is, sorry, C2n, so this is minus 1 to the power n plus 1, and then this is 2 squared, 4 squared into 2 to the power 2n squared, and then 1 plus 2, this is up to 1 by n, or you may try to adjust with this. So from here, what is going to come out? See, it is going to be 2 squared, and this is 2 squared into 2 squared, 2 squared into 3 squared, and so on, 2 squared into n squared. So basically from here you are going to get factorial n squared and 2 into 2 to the power n. Is it okay? Fine? Can I write it like that? Are you getting my point?
Yes, sir.
Right? So this is going to be eventually 2 to the power 2n into factorial n whole square, right? So maybe next line, let me change it to 2 to the power 2n factorial n whole square. So therefore that this series, therefore this series. So what I can do, therefore I can write, therefore your y2 equal to your y1 ln x, and then plus I can write it n equal to 0 to infinity, right? Say it is going to be x to the power 2n, because this is an even order series. So this is going to be minus 1 to the power n plus 1 factorial n whole square into 1 plus half plus 1 by n. And this I am going to adjust with x to the power 2n divided by 2 to the power 2n. So that's it. Okay. So this is one of the application of those, I mean, not really theorems. You can get it from theorem also. You can get it as a derivation also, like how we can put it into use. So in my next class on Monday, I'm going to do a little bit of Gauss's hypergeometric function, hypergeometric equation. And from there, I would like that to lead you to Lysender's polynomial. And after that, I'm going to stop. And today I have already uploaded some materials on Lysender's and Bessel's function. You please have a look at that. And with the help of your Simons and Gill and Cullen, those two books, you please study it on your own. Because if I continue, I mean, doing this power series, then the number of classes is going to be infinite. Okay, I cannot do it because I have some limited time frame during which I have to finish your syllabus. Okay, and again, next time, again, I will start with system of linear differential equations. Of course, I am going to consider only first order linear differential equation system of. So that theory part, which you have already done, the solution part, the initial part, you please study on your own. Definitely, I am going to touch upon that, but I will be more interested in autonomous system of equations, where I'll be able to find out all those critical points, all those concepts. Okay, because we have limited time. Okay, so then I will meet you on which day?
Saturday.
Tuesday.
Saturday. Okay. I'm happy about that. You don't want to bypass that. I thought that you were going to answer that Tuesday so that you don't want to appear in the exam, right? So as you have got the mail, the syllabus is going to be up to 2 days class. And probably, like say, whatever was before quiz 1, that syllabus I'm not going to consider. Even if something is going to come from there, it is only going to be some conceptual. I mean, very short question on that, for which you don't need any preparation. So if you concentrate on whatever I have covered after quiz 1 till today, that should be good enough. Okay, fine. So I will meet you on Saturday.
Sir, what is the second book you suggested?
What is?